the chain rule. This is a derivative rule that is really got to be rock solid if you're going to have any success in this class. Really, just so you know where we're at in your big old calculus education. For the most part right now, you're focusing on developing calculus techniques, derivative techniques, how to take a derivative. Once you get all those techniques in place, think of it like teaching you how to dribble, to pass, to shoot. Well, then once we get all those in place, then we can drop you in a game, which is like derivative applications. So we're still working on that. This is a really big technique kind of skill. The big idea is you use the chain rule when you have a function within a function, which might seem pretty rare, but you'll actually find this is it happens all the time. So sine of x squared plus 1, that's an example of a composite function, one composed on the other, where x squared plus 1 is dropped into the sine function. Follow? When you take a derivative on such a function, you have to be on your game. In order to get there, first of all, though, I want to talk about a couple background ideas that because you learned at this school, they're rock solid. If I asked you to convert 2 meters to inches, you could do that because you're a Saxon student and you would use unit multipliers. I love it. You understand the idea of unit multipliers, which is a chain rule in essence, or a domino effect kind of thing. You would go meters to centimeters, centimeters to inches. Anybody remember the inches to centimeters conversion? Okay, so you're good, and you understand the whoosh, whoosh kind of effect. Now, the idea that meters is not directly related to inches, but there's an indirect relationship. Meters relates to centimeters, and centimeters relates to inches. That's a chain rule. Okay? Think of it like this gear isn't directly touching this gear, but I think you'll agree that as this one turns this way, it causes this one to change that way, which causes that one to move that way, and that one to move that way. Anybody like mechanics and like working with their hands? Someday, oh yeah, cool, okay. I love to tinker when I was your age. I would take stuff apart, sometimes put it back together, but sometimes I just broke stuff. But I was always interested. Now that said, a fraction is much the same way. This fraction isn't being directly multiplied to that, but they're indirectly related. Now let's talk about how this relates to chain rule and how calculus derivative works. So my goal is to say if you have a function like this, a function within a function, which I'll call it a function within a function or a composite function, how do you do it? Now, in order to see this, we're going to do this once the long way, just to see how it works, and then we'll work with the shortcut. And rather than work from the definition of the derivative, which doesn't go very well, I'm going to do it this way. All right? So what I'd like to do is to take that function, sine of x squared plus 1, and break it into 2 pieces. Okay? Sine and x squared plus 1, where I just kind of decomposed it, really. I said, let u equal x squared plus 1, and sine of u then is sine of x squared plus 1. We're supposed to find the derivative. Okay, now, check this out. If I wanted to take the change in y with respect to x, let's start here. I could first say, all right, how does y change with respect to u? So if I said, how does y change with respect to u, that means a derivative. So if I took the derivative here, what would it be in Leibniz notation? dy du. Okay? Now, I'm going to then say, all right, how does u change with respect to x? So if I took the derivative of that, the notation would be du dx. So I have 2 derivatives. Stick with just floating around in space. Well, if I wanted to put those 2 together to figure out what is dy dx, how does y change with x, then wouldn't it be the case that I would just straight up multiply those? Y changes with u changes with x. Indirectly then, y is changing with x. So for this problem then, dy dx is, now let's talk about each of those, what they really would be. dy du, here's y equals sine of u. What is dy du? What's the derivative of y with respect to u? Cosine of u. Follow? And what about du dx? Here's u as a function of x. If I take the derivative of u with respect to x, it's 2x. Are you with me? Hey, whoa, you're freaking me out. All right. Now, that's great. We're getting there. But for your final answer, the original problem didn't have any u's in it. It was y equals sine of x squared plus 1. There was no u. So for our final answer, if we don't want a derivative that has u's and x's, because what the heck, if you look at that, you're going to look at that and say, what the heck, what's u? What's u's come from, right? Instead, then you're going to go back and sub back in for u, so it's all in terms of x. If you do that, then instead of cosine u, you're going to replace u back with what we said it was, which was x squared plus 1. Now that is the derivative of sine of x squared plus 1. Now, that's great, but I don't want to do all that u substitution stuff, and you won't. So instead, let's talk about what we really did there. I'm going to write this again. dy dx is cosine of x squared plus 1, given that y is sine of x squared plus 1 times 2x, right? Now, if you were to look at this and put this into plain old English so you can explain this to somebody in more about common sense or layman's sense, this was the original function. The derivative was, first of all, cosine with x squared plus 1 still in it. Now, how does that relate to the original problem? Cosine came from taking the derivative of the sine. All right, now I'm going to say that as the derivative of the outside function. Wasn't sine the outer function? So we took the derivative of the outer function with the inside the same, staying the same. I just took the derivative of the sine part, which was cosine. X squared plus 1 just stayed the same, stayed inside x squared plus 1. You follow? But then I multiply that by, and what did 2x come from? That's the derivative of the inside times the derivative of the inside. Now that then is the chain rule. It's the idea that if you have a function that is a function within another function, which is sometimes called a composite function, then you take the derivative this way. You take the derivative of the outside function, which is f prime, with the inside the same. Then multiply that by the derivative of the inside, which is g prime. So let's say we do this, a problem like we will be doing it forevermore, without this u substitution. If I ask you to use the take a derivative like this by chain rule, you don't do this u thing. Okay? I just wanted you to see why you do what you do, but now we're going to use this idea. So if I take the derivative on this, let's first understand what's outside, what's inside. What's the outside function? The outside is the e to the x, yeah? And what's the inside? X squared plus 2x. So when I say we're going to take the derivative of the outside, it's the derivative of the e to the function. And what is the derivative of the e to the function? E to the, with the inside still the same. So it's still e to the x squared plus 2x. Then I multiply it by the derivative of the inside. What's the inside again? X squared plus 2x. So what's the derivative of the inside? 2x plus 2. That's the derivative. Now for E, it's a little wacky because you can't tell if it was the original or took the derivative. So let's try one that's a little different. You try this guy. For this, what's the outside function? Log, and what's the inside? X squared minus 6, all right? Use the chain rule, using proper notation like y prime or dy dx to take the derivative. Ready? Okay, so first couple days is kind of the same common mistake happens a lot. People will say, oh, the derivative is the derivative of the outside, the natural log. Well, the natural log derivative is 1 over x times the derivative of the inside, 2x minus 1. Pretty common. But they're forgetting one part of the chain rule, which is to say it's the derivative of the outside with the inside still in. So when you say the derivative of log is 1 over, it's not 1 over x, it's 1 over whatever you took the derivative in what was inside the log. So what was inside the log? X squared minus x. The derivative of the log is 1 over what was inside before, 1 over x squared minus x. Then times the derivative of the inside, 2x minus 1. That's what your derivative is to look. How'd you do? Yeah, okay. The most missed chain rule problems. Do I have a? I think these notes are a little. What do I have for you? Do I? Is this what you have? You have 2 problems. I thought I made some change. I wrote my note to myself to change this a little bit. What are your 2 problems? Y equals e to the negative x, and the other one is with a 2 or something. Sine of 2x. All right. So let's be clear. People tend to think, oh, it's not a chain rule if it's not 2 functions. Like the previous problem, people see that as a chain rule because obviously there's 2 functions going on, log and x squared minus x. But people think that this is not a chain rule problem because it's kind of just a plain old x. Well, that's not the case if this isn't anything but just a plain old x to the first, 1x to the first, then it's chain rule. It's a function within a function. It requires chain rule. So if I were to take the derivative of e to the negative x, I'd say, all right, what's outside? What's the outside function? E to the x. And what's the inside function? Negative x. All right, so when I take the derivative of the outside with the inside the same, the derivative of e to the negative x, the outside with the inside the same is e to the negative x. But then times the derivative of the inside. What's the derivative of negative x? Negative 1. So it wouldn't just be e to the negative x, because e's derivative is itself, but there's also a chain rule component. It would actually be negative e to the negative x. You follow? Try the other one then. Take the derivative of y equals sine of 2x. That is a function within a function, because 2x is not just plain old x, there's more. Mr. Lowry, what's the derivative of sine?
Cosine 2x times 2.
Beautiful. Okay, the derivative of the outside is cosine with the inside the same, 2x, but then derivative of the inside, you pick up the 2. Cool. Let's talk about little variations on this. Instead of, these are called analytical derivatives. They're the derivative of an equation. Sometimes you'll apply the derivative to a table or a graph. So let's do different representations of this idea. So you have this big old table of at two different x values, what f, g, f prime, and g prime are. You see where I'm coming from? The question is, evaluate the derivatives with respect to x for, actually I'm giving you two different problems here. We'll do this one together. So I want the derivative of f of g of x at 0. Is that clear? So the derivative, I'll just call it the derivative of that thing. I'm not sure what, it didn't give me a name for the function, so I guess I'll write it this way. I'm going to take the derivative of this thing eventually at 0. First I have to take the derivative, and then the second step I'll do with the 0. Okay? So, by chain rule, what's the derivative of a function within a function? F prime f of g of x, the derivative of the outside with the inside the same, times g prime of x, and we need to evaluate that at 0. That a little evaluation bar means, all right, now put in a 0. You with me? Now students want to do this so quick. Students are always go, 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 and old people are slow, slow, slow. But that's what I want to do. I want to put in 0, working inside out. Do I first do f prime, or do I first do g at 0? I need to do g at 0 first. G at 0 is? Now we're looking at the table. Okay, so g at 0 is 1. That 1 now will need to be put into f prime. You follow? The other part of it is g prime at 0. What's g prime at 0? 1/3. Finally, I can find f prime at 1, and that is negative 1/3. Negative 1/3 times 1/3. Run it in for the touchdown. Don't fumble now. It is negative 1/3. You see? Try 11, please. Right. Are we ready? No. This one's kind of like herding cats. You gotta keep everything together. Don't lose any. Let your eyes get scratched out. All right. So here we go. I say the outside is blank to the negative 2. And the inside is the sum f plus g, or g plus f. You follow? So when I take the derivative of the outside, what's the derivative of blank to the negative 2? Negative 2 comes down, I drop the exponent 2, negative 1, negative 3. 1 less than negative 2 is negative 3, negative 1. Okay, so negative 2, blank, drop it to the negative 3. The derivative by chain rule is the derivative of the outside with the inside the same. So what's in here? Inside the same means g plus f is still in there. You follow? Times the derivative of the inside. What's the derivative of the inside? G plus f. Talk to me, people. What's the derivative of g? G prime. And what's the derivative of f? F prime. And can I take the derivative of a sum by just taking each piece individually? Yes, you can. Now then, that needs to be evaluated at 1. So here we go. So let's go here. Do you feel like this is negative 2 over something cubed, yeah? Isn't that what a negative exponent means? And what is g at 1? Negative 4. And what is f at 1? 3. All right. Got that. Now, parentheses, what's g prime at 1? Negative 8/3. And what's f prime at 1? Negative 1/3. Okay. Let's see how we did. That's negative 2 over negative 1 cubed is negative 1 times negative 8/3 minus 1/3 is negative 9/3. So when it's all said and done, it looks like positive 2 times negative 3. Do you win with an answer of negative 6? Did you win? Or did you take the L, as you kids say? Yes? All right. Well, I hope you won. You are tied. All right. Using the chain rule graphically is what it should say, not graphical. Graphically. Graphically, use the graph of f and g. Do you feel like you could give this a go on your own? All right. Give it a go. Worst thing you can do is fail. Anytime they ask you for a numerical derivative, you should first show the general derivative, then the second step show the numerical. Do not ever go straight to that. your answer is?
1/3. Oh. 1/3. I got 1/3.
How come I got?
I don't like it.
How come I got 3? Okay. I feel like maybe I made a mistake because you all say negative 1/3, 1/3. So authoritatively, maybe I made a mistake. So do you agree with F prime G times G prime for the chain rule? Okay. So H prime is F prime at G of -4 times G prime at -4. Cool? All right, so the inside of this, G at -4 is, oh, I looked at F, didn't I? Yeah, you're right, not bad. You win, okay. Well, maybe you win, we'll see. I definitely lost. All right, so I looked at the wrong graph. Here's, even though mine's colored, for Pete's sake. So here's G, I agree. All right, so G at -4 is 2. Cool. So I'm going to replace G at -4 with 2, and I'll deal with that prime in a minute. What about G prime at -4? I also did that wrong. I looked at the wrong graph there, too. What'd you say for that? -1. Okay. Looks like you're winning. You're leading the competition now. What about F prime at 2? F prime at 2 means the slope of the F graph at 2, and it's down 1/3. So that's -1/3 times our -1, 1/3. Yay! Nice job. All right. Now, I said for the most part we're going to focus on technique, but we can do some applications. One application now is to find an extrema using the chain rule. So if I said use the derivative to find and justify a relative max by the first derivative test on g of x, then what would you do? First of all, how do you use the first derivative test? What's the first thing you do? Find the derivative, all right? Tell me, why is this a chain rule derivative? The deal of the day is it's a function within a function. You could look at it as 4 minus x squared to the 1/2 power. It's a function within a function. So what is the derivative via chain rule? What's the outside? The outside function is what? Jake? Square root function. The inside is what? Mr. Deuce? 4 minus x squared. Cool. So when I take the derivative of the outside, Ms. Harrington, what's the derivative of the blank to the 1/2 power? Or just give me the whole derivative. How about that?
1/2. And then 4 x minus 2
4.
I don't know, I'm confused.
Okay, sorry. No worries. The derivative on the outside is the half comes down. Don't worry about the inside right now. The derivative of the half is half comes down and we drop the exponent to -1/2. Cool. And the inside stays the same. Then we multiply by the derivative of the inside, which is 2x minus, nope, sorry. What's the derivative of 4? 0 minus the derivative of x squared. Thank you. Okay, cool. So I want to know where this is 0. Technically also undefined, but we'll talk about that later. That's pretty gross. Can you tell me, how can I clean that hideous G prime up? What's another way to write it cleaner? Because you want to write it cleaner. Sam, what would I do to write that cleaner? Wonderful. All right, so this is the same as 1 over the square root of 4 minus x squared. Then the half would mean a 2 down here, and the -2x, that's not a negative exponent, so it's in the numerator. Are you with that much cleaner version, people? All right. Is this going to be 0 when the top is 0 or the bottom is 0? Yeah, a fraction is undefined if the bottom is 0. So this is 0 at x equal 0. It would be undefined at 2 and -2. What that means, we'll talk about that also. All right? So now we're going to talk the G prime, not F, but G prime's behavior around 0. Less than 0, like a -1, here's the derivative. I think this is probably the easiest place to look. At -1, what's the top? Positive in the bottom. Still positive, yeah. So overall, what's G doing before 0? Increase, okay? And after, say at +1, what's the top? Negative, the bottom? Positive, and so what's G doing afterwards? Decreasing. If G went from increasing, then went flat, then decreasing, what did I see at x equals 0? Yeah, so let's conclude it. G has a max at what? X equals 0, why? Because G prime changes positive to negative at x, positive to negative, and that I already said where, okay? So this is a little bit of a stinker here. What if you said in your conclusion, G has a max at x equals 0 because F prime changes positive to negative? There's 1 point built into the conclusion on the AP test. Would you get that? No, because you said G has a max because F prime changed from, what's F? Is there an F here? Yeah, no. So does that matter? Yeah. If you use the wrong letter, you're out. They don't care if you say, oh, you meant F. There's no you meant. You say it's just like I don't call you Jimmy. Okay. If the name of the function is G, call it G, not F. You have to use the function name that you're given. If you fail to do that, you're wasting your time. There's 1 point and you lost. All right. So be careful. Make sure you use the function name. F is most common, but it's not always. Okay, you with me? Talk to me, what's the shape of this graph? You should know, just to confirm. Yeah, isn't it y equals the square root of 4 minus x squared, y squared equals 4 minus x squared plus y squared equals 4. Is it the full circle, though? No, it's only the top half. Does it make sense, then, that there's a max at 0? Yeah. Furthermore, there's actually mins at -2 and 2 because the graph goes vertical. Those are also critical numbers, but we'll talk about that later. It just said find the max, so we did that. All right? Cool? That is the idea. So when you use the chain rule, you have a function within a function. And how do you take a chain rule derivative? You're in the outside. Perfect. All right, cool. The homework you'll find, some of my extra practice or fun sheets are humdingers, but this one is not. It's pretty straightforward. I would bet it can be done in a half hour. Questions on last night's homework? Set 33, was it? The test is scheduled for next Wednesday, by the way. What? 2 and 3? That's kind of 2 and 3. Am I right? Okay. 2 and 3. 23 rather. Sorry. I listen like a teenager. 23. Any other questions? 1? Did somebody say 6? I thought it was 6. Never mind. 1, 23, and 1. All right. Here we go. Okie dokie. Is either of these a replacement from 23? Yes. All right. So 23, I will actually put together a whole day of practice on movement. Movement is not a little part of this class. It's actually a huge part of this class. And right now, I'm just kind of putting problems on there without giving you instructions. So I'm glad you're asking. The idea is you're given the position of a particle function, and it's moving side to side. Think of it like moving along a number line. So For example, at time equals 0, what's the position? You would say it's at 0, yeah? And at time equal 1, the position is at -4. 4 seconds later, it's here, so it must have moved this way. And then at time equal 2, it's 4 minus 10, so it's at -6. So it's still moving this way. But if you look at time equal 5, it's 25 minus 5, the position is 0. So later on, you'd see it's back here, so it must have moved back that way. The idea then is it's moving left and right. How do we figure out when it's moving right? Well, think of it like, first of all, moving right needs to be translated into calculus. Moving right means the position is increasing with time. And we are starting to talk this week about how if a function is increasing, then its derivative is positive. So position is increasing with time means the derivative is positive. What is the derivative of position? Velocity. Velocity is positive. So when you're talking horizontal movement, if the velocity is positive, it's moving right. If the velocity is negative, it's moving left. If the velocity is 0, it's temporarily at rest. So we are going to find, first of all, the velocity, which is the derivative of the position. You've got to communicate that. This is dangerous because the more you get comfortable, the less likely you are to write that. You'll start to say, well, everybody knows that velocity is the derivative, and you just go there. But that doesn't cut it. You have to communicate the calculus. Velocity is the derivative of position, and then say, here it is. All right, you follow? No. If I want to know positive, then I mean sign test. And sign test starts with zeros. You agree that the velocity is 0 at time equal 5 halves. How is this particle moving then at 5 halves? It's momentarily at rest because it stopped moving there. So I would imagine that's the great dividing line between when it was moving left and then started moving right. It must have been at time equal 5 halves. It did that. Now, if I sign test the velocity, which is, again, the p prime function, then before 5 halves, maybe times 0, that's negative, implying that the function is moving left. And after 5 halves, maybe time 100 billion, that's positive, and therefore moving right. The last thing is to say it well, to know what to do with the endpoints. If I want to know when it's moving right, with justification, you'd say the particle is moving right on what interval? 5 halves to infinity. Do I include, obviously you don't include infinity, you never do, but 5 halves. Do I include 5 halves or not?
Yeah.
Why not? Yeah, it's at rest there, so it's not moving right then, it's not moving at all there. So it's 5 halves to inclusive. Why do you say that? Because you could say it one of two ways. Because the derivative is positive, or you could say the velocity is positive. And you could say the word positive, or you can write greater than 0, you can put a little plus sign, all those are good. Okay? Good question. Number 1. Is number 1 still a question? Okie dokie. Okay, number 1 is without change. Rectangle is shown and find the area of the triangle. Oh, this is a good one. I didn't think this. It didn't occur to me that this would be true, but it's pretty cool. All right, so there are many triangles that you could make that inscribe the diameter, like this, or like this, or like this, or like that, or so on. all of these are that same kind of situation, yeah? A right triangle is inscribed. Now, every one of those, I might not look like it, but every one of those has a right angle there. And that's because if this arc is 180, it doesn't matter where that angle falls, it's got to be 90. All right, now that's great, but I'm going to look not at these guys for my area, but this for my area. Okay, do those all have the same area? Or do you reckon as this triangle gets closer and closer and closer to the axis, that area actually gets smaller and smaller and starts to approach 0. So I don't feel like they have all the same area. So it must be variable. But let's just start here. Base times height divided by 2. Don't use the right angle here for the base and height. Instead, use this base. What's the base? The base is always 2x, yes, but if it's the unit circle, then what's the radius of the 1 unit circle? The radius is 1, so the diameter is 2. The base of all those triangles is 2. Now the height, I think we'll agree, is the right angle distance up from the base. So whether it be here, or here, or here, or here, those are all varying, but what is the height? What do we call a variable distance up on the coordinate plane? We call it y. All right? At this point, y is, a half. At this point, y is 0.3, and y is 0.8, and y is 1. So the height is always 1. In that case, the area is exactly equal to the y. The area equals 1. In this situation. Feel free to ooh and ah at that. Pretty cool, huh? Or not. Just silently ooh and ah. You don't want to look like a nerd. All right. Any other questions on 33? 14? Okay. 14 is add D for practice storing an intersection point. Okay, so I'm going to need my calculator here. This is good stuff. Intersection points are not just pre-calculus skill, they're actually going to be a huge skill to definite integrals, so I'm trying to remind you or keep that skill alive. So number 14, the first thing I need to do is graph the top half of this. Oops, let's go back here. The equation was x plus 4 squared plus y plus 4 squared equals 12 squared. Right? So if I want to graph the top half, I want to solve this for y. So if I take y plus 4 squared and call it 144 minus the square of x plus 4, and then y plus 4 is plus or minus the square root of 144 minus x plus 4 squared. Don't you even think about square rooting each of those parts individually. That's 100% not true. And then y is negative 4. Now if it's top half, bottom half, then the top half would be negative 4 plus to the top. So that's the first part of the problem. Solve the equation for y in terms of x and take the top half of the circle, which is the positive y. Plug that into your function. Negative 4 plus square root of 144 minus x plus 2. Is it plus 2 or plus 4? plus 4 squared. All right, I might zoom out a little bit. Okay, very cool. Now I think it said in the rest of it graph 16 over x, if I'm not mistaken. 16 divided by x looks like that. It says don't worry about the third quadrant part. Find the coordinates of the intersections in the first quadrant. So if I find the coordinates of the intersection points, analyze graph, intersection, here to there. All right? Now here's the part that I added to part D. You need to be able to store those points for later use. We're going to care about the x. So how do I store that x? So you hover over it, click it, and then go to vars and store it. Let's call it A, shall we? I'm going to do the same thing with the second intersection point. So watch it again. Menu, analyze graph, intersection, show where you're finding it. Okay, now I'm going to store that x value. Again, I put the pointer over it, click, vars, store variable, enter, call it B. Don't forget what you called them. Those are now stored, bold indicates they've been stored. You with me? We good? Okay, now I want the derivative of the function at that point. Does it say the derivative of the circle or the derivative of the 16 over x? It says the circle, okay? So go back to your home screen, and we're going to have the derivative. Menu, calculus, derivative. We want the derivative at what value? What did I call it? A. I called it A, or B. I called it A. Then I have two graphs stored in there, the semicircle and the 16 over x. F1 was the semicircle. So the slope of the curve, the slope of the circle at that point is negative 0.67. So y prime at 2.680 is approximately negative 0.670. You see where I'm coming from? Okay, then y prime at the other intersection point. What was the other intersection? You get that. Okay, good calculator skills there to be had. Have a great weekend, people. In here, start working on your college stuff. You know you should. Get those letters of profile letters done so your teachers can write the letters of recommendation. All that good stuff. Juniors, enjoy just having physics. All right.
Yeah, I agree.